So in the last couple videos, we looked at a couple different kinds of improper integrals. And what we want to think about now is what happens if you have a really nasty function that you're just not able to integrate, or anti-differentiate rather. And so we want to think about this idea where, oh, you have some function that's heading off here. Let's call it f of x. And let's say you found the integral from 1 to infinity of f of x dx. And you found that it was, say, c, some number. So you saw that it converged, and you saw that it converged to, say, some number c. And let's suppose that you have some other function. Let's call that function g of x. And you know that g of x is squeezed between 0 and f of x. Then we should be able to conclude that the integral from 1 to infinity of g of x dx is also converges to something that is between 0 and c. Okay, so basically we're just saying, hey, if we've got a function that's less than another function and the area under that function converges, then the other one has to converge as well. But we need some things to compare to, and so let's investigate something that we'd like to compare things to before we move on to some examples. So let's take, for instance, this right here. The integral from 1 to infinity of 1 over x to the p dx. Now we saw a couple examples of this. We saw the integral from 1 to infinity of 1 over x squared dx. We saw the integral from 1 to infinity of 1 over the square root of x dx, which would be x to the 1/2. So we already saw that for p equals 2, this converged. And for p equals 1/2, this diverged. But we'd like to know for sure for what p values this converges and diverges. So there are really two cases of this, because if p is 1, you get the integral from 1 to infinity of 1 over x dx, and that's going to use the natural log. And if p does not equal 1, then you are going to use the power rule. And so we're going to look at two different cases here, because one of them uses the natural log and one of them uses the power rule. So for the natural log case, let's set up our limit and say the limit as b approaches infinity of the integral from 1 to b of 1 over x dx should equal the limit as b approaches infinity of ln of absolute x evaluated between 1 and b, which is the limit as b approaches infinity. Since b is approaching infinity, I can drop this absolute value sign and just say ln of b minus ln of 1, which is just the limit as b approaches infinity of ln of b, since ln of 1 is 0. And so now I just need to think, well, what happens to the natural log as the input approaches infinity? It also approaches infinity, more slowly, but it still approaches infinity, so this diverges. So we know for sure that for p equals 1, in other words, for 1 over x, it diverges. Now let's see what happens with 1 over x to the p where p does not equal 1. So then this would be the limit as b approaches infinity of the integral from 1 to b of x to the negative p dx, which is equal to the limit as b approaches infinity of x to the negative p plus 1 divided by negative p plus 1, evaluated between 1 and b, right? Because I am adding 1 and then dividing by that exponent. That should be the limit as b approaches infinity of b to the negative p plus 1 divided by negative p plus 1 minus 1 to the negative p plus 1 divided by negative p plus 1. I could factor out the 1 over negative p plus 1 if I wanted to, because it's not affected by the limit as b approaches infinity. And this becomes b to the negative p plus 1 minus 1. So really what I'm curious about is this right here. Does this head towards infinity or not? And what values of p would make this thing head towards infinity or not? Well, what I want to think about is what needs to happen in order for this to converge and what needs to happen in order for this to diverge. And so I want to think about a couple cases here, really. Essentially, what I want to think about is for b to the negative p plus 1, what I want in order for this to converge is I want negative p plus 1 to be less than 0. If the exponent is less than 0, then I'll end up dividing by that huge number, and that will send this piece to 0. If the exponent instead is greater than 0, then I'm just doing b raised to some power, and if b approaches infinity, it's going to approach infinity as well. Even if it's less than 1 and it's slow, it's still going to approach infinity. So here I would get negative p is less than negative 1, so p is greater than 1. This would be to make it converge. And here I would get negative p is greater than negative 1, so p is less than 1 to diverge. So before we saw that if p does equal 1, it diverges. If p is less than 1, it diverges, which matches up with what we saw with p equals 1/2. And if p is greater than 1, it converges. So we can now conclude that this right here converges if p is greater than 1 and diverges otherwise. So that can be helpful because that is going to allow us to compare some other improper integrals to this improper integral. And this is going to have some applications later on when we are considering some infinite series, which are very closely related to improper integrals. Improper integrals are sort of like the continuous version of a discrete series. So let's consider this example right here. We have the integral from 1 to infinity of 1 over the square root of x cubed plus 5 dx. And we want to know, does it converge or does it diverge? So I don't know how to find this antiderivative, but what I can think about is what this is similar to. So 1 over the square root of x cubed plus 5 is pretty similar to 1 over the square root of x cubed, right? And this is equal to 1 over x to the 3/2. And that looks a lot like what we just decided converges or diverges. Now this right here converges because 3/2 is bigger than 1. This, I added 5 to the denominator. I actually didn't add 5 because it's in the square root, but I added 5. I added to the denominator in some sense. And when you add to the denominator, things get smaller. So this is less than this. That's good. Now I can basically say, since 0 is less than or equal to 1 over the square root of x cubed plus x, which is less than or equal to 1 over x to the 3/2, for all x greater than or equal to 1, and since the integral from 1 to infinity of 1 over x to the 3/2 dx converges, so does the integral from 1 to infinity of 1 over the square root of x cubed plus 5. I don't know what it converges to, but I know that it converges because this friend converges This friend is less than it, so it has to converge as well. Okay, let's look at one more example and then we'll be done with this. So let's consider the integral from 4 to infinity of 1 over ln of t minus 1 dt. So this is a lot like 1 over ln of t. It's not exactly like that, but it's similar to that. Now, just thinking about this a little bit, ln t does not grow very quickly, and so 1 over ln t is not going to get small very fast. So I think this might diverge. So let's think about this for a second. 1 over ln t minus 1 is greater than 1 over ln t because subtracting from the denominator makes something bigger. And that is greater than 1 over t because t is bigger than ln t for t, greater than or equal to 1. So is that true? ln of 1 is 0? Yes, that's true. T is greater than or equal to 1. I'm pretty sure that's true. So basically what we have is this bigger than this, bigger than this. And what we know is that the integral from 4 to infinity of 1 over t dt diverges. It really doesn't matter that we started at 4 instead of 1. We're just subtracting finite area off something that was infinite, so we don't really care about it that much. And if this diverges, and 1 over ln t minus 1 is greater than 1 over t for all t greater than or equal to 1, then the integral from 4 to infinity of 1 over ln t minus 1 dt also diverges. So we didn't really talk about this in the beginning, but clearly, I would say, if you have something that diverges to infinity and another function that is just bigger, then it will also diverge towards infinity. So this is what we call comparison of improper integrals, and it allows us to analyze some interesting infinite integrals.